We're going to pick up where we left off and look even at greater detail at unit generators and their implementation within Nyquist. Unit generators typically do their processing incrementally. Again, we talked about how samples or sounds can be really very large. And so it's desirable not to compute an entire sound in memory and then pass it as a parameter to a function. Instead, you'd like to avoid computing it altogether, but when you do compute it, you typically compute it incrementally. So you compute a sample or a block of samples and pass that on to the next unit generator. It operates on a block of samples, passes it on, and eventually a sample or a block of samples comes out the output, and then you make another pass and compute the next sample or the next block of samples. So if you're doing things incrementally, sometimes this is called stream processing or just incremental processing, but you need to store information from one block of samples to the next. So for example, the current phase and frequency of an oscillator at the end of one block has to match the phase and frequency at the beginning of the next block. So therefore, unit generators are implemented as objects in the sense of object-oriented programming within Nyquist. So they have and they retain some state information. These objects are accessed implicitly to provide samples. The objects themselves are hidden from the user. And this is different from most other music programming languages that expose or present the unit generators as an explicit graph that's visible as a graph to the user. And in those systems, you construct the graph, and then the system makes multiple passes over the graph to compute sounds and propagate samples to the output. Then you make another pass to get the next block of samples. You can see this especially clearly in Max MSP, which is a graphical programming language for sound synthesis. The unit generators are actually shown visually, and the connections between them are visually manipulated or graphically manipulated and visually displayed. So that's a good example of a very non-Nyquist approach where the unit generators are all out there to see and to work with. In contrast, in Nyquist, there's no direct access to unit generators as objects. Instead, we use functions and function calls to make and return objects called sounds. And instances of unit generator objects are contained within the sounds, and they're called upon when samples are needed. So this gets back to the lazy evaluation idea. A sound is this abstraction that represents a sound, a big collection of samples and some other information. And when you need to access the samples in that sound, then the unit generators are called upon to do their computation. And we'll learn more about sounds later. When you play a sound, so for example, you write play some sound expression, the expression returns a sound, which again internally is going to be a graph of unit generators. Probably the sound that you play is constructed by combining many other sounds. And so you have a whole graph or a whole tree of sounds that have the potential for computation. So to play the samples, Nyquist has to traverse this graph and generate samples incrementally, exactly like Max MSP or some other unit generator-based language. The samples are computed in blocks of about 1,000, and they're played essentially in real time from Nyquist, as long as Nyquist can keep up. One of the interesting possibilities is that instead of just playing a sound, you can write set variable equals sound expression and compute a sound and assign it and store it in a variable. And then you can reuse that sound many times. But if you do that, the entire sound might be computed, saved, and stored in memory. In some cases, that's a great thing because it's pre-computed, it's reusable. In other cases, if the sound is really large, that's a very bad thing because you've filled up your memory with samples, and that can cause really bad performance. So in general, we do not want to assign sounds to variables or store them in variables, particularly global variables. We want to just combine expressions and ultimately play them, and that's when they get computed.